Hello again. We're continuing with waves. Now, before we get going with everything I want to show you, I want to point out right up here that these are the answers for some questions that are going to come up at the end of the video. So when you get to the end of the video, you answer the questions, come back here to check your answers. All right. So we're talking about waves, and at this point, I want to show you a variety of things from this simulation. This is coming from the phet.colorado.edu website. Phet is P-H-E-T .colorado, like University of Colorado.edu website. And okay, so what this is showing you is a simulated spring, and I can control the speed at which waves go with the tension. So right now, if I do this, you can see that the waves go very slowly. If I make the tension higher, like this, then the waves go faster. And that's something that we learned in the previous video. Of course, if I make the tension low, then the waves will go much slower. That's agonizingly slow. Now, another thing I didn't mention in the last video is damping. So damping is friction, and we talked about damping in the last video I made for oscillations, the video where we talked about the quality of an oscillator. Well, this is very closely related. It's the same type of friction. It's the kind of friction where the speed of the things going up and down, this whatever this is made of, its speed determines how much friction. And it's the friction is, the direction is always in the opposite direction from whichever way these particles are moving. So if they're moving up, the friction is downward. If they're moving downward, the friction is upward. And that's the nature of damping. If I have zero friction, then these waves will just go forever. They'll never stop. On the other hand, as soon as I have a significant amount of friction, then the waves stop. Now, the waves have energy, and what's going on here in real life, this is a simulation, but in real life, there's always going to be a little bit of friction, and that converts the energy that's in the wave to heat. So you end up just heating up the environment, the air. Okay, so it's convenient for me to set the damping to some reasonable number. Now, here's another thing I want to show you. Usually, we think of waves as being like sinusoidal, right? Like this is these are sinusoidal waves. I'm going to go back to manual here. The waves don't have to be sinusoidal. You've already seen me make pulses, right? That's, you know, a perfectly legitimate wave form. I can make square waves. Here, let's do that. I'll make a square wave. So for a square wave, I go up and down. It's not exactly square. That's probably because of the damping. But yeah, the waves can go downward like that. I can make a wave with, let's say, 2 pulses, and so on. So later on, we'll talk about the formulas that describe waves, and these formulas that describe waves are solutions to a calculus thing called the wave equation. And the tendency is for us to talk about sinusoidal solutions to the wave equation, but in fact, they don't have to be sinusoidal. They can be any shape. All right. Now, let's get to the thing that is the subject for today's lecture, which is going to be, at first anyway, reflections. So in this simulation, the end of our string is is not attached. It's like it's as if it was connected to a perfectly slippery pole. And so when I do a positive going pulse, the reflection is also a positive going pulse. Okay. On the other hand, if I were to fix the end like this, so this clamp here represents a fixed end, and I make a positive going pulse, you can see that the reflection is inverted. Instead of a positive pulse after the reflection, it was a negative pulse. Now let's do that again with maybe a little bit. So there you go. And now it's inverted. Yeah. All right. So that gets us to this place here. And here I'm explaining reflections. So I'm saying, well, if we were to talk about waves that are sinusoidal, it gets a little difficult to explain what a reflection is doing. It's a little bit easier if I talk about a single pulse. So here I've got a single pulse. It's moving to the right. And here I've got the pulse just before it hits the end. And this represents an attachment to a wall. So this would be a fixed end. And after the reflection, the pulse is the mirror image, the up and down mirror image of the original pulse. We say it's inverted. On the other hand, if you have a pulse going to nothing, the end of the rope or spring or whatever is attached to quote unquote nothing. Now, to be honest, nothing doesn't work very well because you need something to maintain the tension in the spring or in the string. So really, instead of nothing, what I should have said is that the end of the string is easily going to move up and down without any friction or anything, but the end of the string is not allowed to move left and right. So that's maybe better. Maybe I should change my notes. Anyhow, after you come to a free end, the pulse is reflected, but the pulse shape is identical to the original pulse shape. It's we call that a non-inverted pulse, a non-inverted reflection. And this ability, this is something that is important in our technology, in optics and making lasers and so on. And the one place where you guys will see it a lot is in the anti-reflection coatings of glasses. And so what's going on is the light, when it hits glass or plastic or whatever these glasses are made out of, they are going to the light will the light waves will be inverted. But if you can add a layer of something that will somehow cause a non-inverted pulse to also happen, then we'll be able to see later on in maybe the next video how the non-inverted pulse plus the inverted pulse can be put together and they can cancel each other out. So that's something that's going to come up in a little while. All right. Now we come to something which is probably going to be a bit confusing for you. It's hard to understand, it's hard to teach, so if you don't understand this at first, check out the book. The book has, pretty good explanations, and then maybe come back to this to try to understand it. So, the mathematical representation of waves traveling. We're going to be thinking about sinusoidal waves, but like I said before, they don't have to be sinusoidal, but for this, we're going to be talking sinusoidal. So we're talking about a disturbance which is represented by cosine omega t. and A represents the amplitude of the disturbance. So if we're talking like water waves, it would be how far up the wave goes or how far down. That's the A. And the omega is the frequency in radians per second. And now you can convert between radians per second and cycles per second by a factor of 2 pi. So omega equals 2 pi f. And so the convention is to write things this way. So we have that the y, the displacement of the wave up and down is a cosine 2 pi over the period, capital T, times time. And T here is like the ticking of the stopwatch. And in Mother Nature, time doesn't stop, right? Time just keeps going and going and going. You can't just stop time. You can make it look like that, you know, with a snapshot or screen freeze or something like that. But in real life, time doesn't stop. Now in space, so y is the up and down location, just like y is the same y here, the same y here. But now x represents how far to the right we are talking. So x is getting bigger and bigger. You're moving more and more to the right. And the wave is a sinusoidal wave. I know it doesn't have to be, like I just said, but for this discussion, it's a sinusoidal wave. And it's 2 pi over lambda. Lambda is the wavelength, and times where you are, x. Now, the reason why it's 2 pi is that the wave, this represents the wavelength, right? So if you have a wave that's doing like this, all right, and let's say going from here to here, in order for the cosine function to go from its maximum down and then back to its maximum again, the input to the cosine function had to increase by 2 pi. So this is a wavelength, and to get what's going in, right, this is the input to the cosine function, you need the cosine to, what goes in, to increase by 2 pi. So to increase by 2 pi, you want x to increase by this much. Well, that much is a wavelength, right? So you want x to have increased by a wavelength. So lambda over, oh, now things cancel. And so, okay, yeah, you've increased the input to the cosine function by 2 pi. I know this is hard to follow, actually. I understand that. But maybe if you read the book, and maybe if you just stop and kind of like settle down and look at the notes and think about it on your own, it'll start to make sense. I don't expect you to get this all, boom, right away. Having said that, we now have two expressions for the wave that we're going to put together. So here we've got the expression for the wave as it behaves regarding time, and for here, for how it behaves regarding to the x position, and we put them together. And so now we have that y, which is, how far up or down you are, is a function of two things. It's a function of x and a function of time. And so when you put it all together, it's a cosine 2 pi over the wavelength times x minus 2 pi over the period times the time. And you're probably wondering why there is a negative sign. We're going to get to that. This represents a wave moving to the right. Now, if instead of a negative sign, there happened to be a plus sign, like I have here, that would represent a wave moving to the left, which seems backwards, right? I mean, yeah, minus, going to the right, that's the positive direction. This doesn't make sense. Well, okay, believe me, you need a plus here to make a wave that goes to the left. You need a minus here to make a wave that goes to the right. All right, now the explanation as to why this backwards seeming thing works is right here. All right, so let's see what I've said. As a wave moves, a point on the wave represents a constant value going into the cosine. So here I've drawn a point, all right, and I'm making the point move with the wave. You know, like this might be a surfer on ocean waves, and so he wants to be on that downward slope of the ocean wave, you know, to keep surfing. So here he is a little while later, and here he is a little while later, and here he is a little while later. Now, this place, right? It represents a number that is constant going into the cosine. So you see, time is increasing, so time is getting bigger. But we said, oh, this is a constant, right? Well, if this is to be constant, you need to cancel out the thing that's getting bigger. Well, to cancel it out, you want this part to be doing something, right? So let's say that this became, I don't know, let's suppose that this piece here became, I don't know, let's say this was 10, right? Well, you would want this part here to also be 10, right? 10 is just a number I'm pulling out of the air. But look, it's going to work because 10 minus 10 is going to be 0. Okay, so maybe that was our situation here. Okay, now let's say the time has increased, and now this stuff here is, because time got bigger, now it's 20. Oh, well then to make this cancel out, this has to be 20. Oh, but in order for that to, for this increase to happen, x has to be bigger. Oh, well, that's what's happening here. Okay, so now x, we're a little further to the right, so x got bigger, and so on. So as t is getting bigger, x has to get bigger, and that makes the wave move to the right in the positive direction. On the other hand, if you have a plus sign here, then as t gets bigger, as this piece here gets bigger, this part over here, right, because we have a plus sign, this part here has to do the opposite. It has to get more negative. And so in order for this explanation to function, you've got to have your wave moving in the negative direction. Okay, that was complicated, and I hope you understand it, but if you didn't, don't feel too bad, because I understand that this is not the easiest thing to get, all right? You're just going to have to work at this a little bit to wrap your brain around it. Now, even if you don't completely understand it, you can still use these formulas, and so that's what's going on in this example. So in my example, I've got that y, which is again a function of position and time, happens to be described by, this wave happens to be described by this, 20x minus 100t. And so maybe as a homework problem or an exam problem or something, I'll ask you to tell me, what is this wave? Maybe draw a picture of it. So you're going to have to figure out certain stuff about it. Now, the approach that you need to take is a kind of a comparison approach. See, the 100, the 20. This 20 here matches up with 2 pi over lambda. That's what I'm saying here. You see, if I want to figure out the wavelength, I use the fact that these match up, that 2 pi over lambda equals 20. And then, you see, I can now solve for lambda. Lambda is I multiply both sides by lambda, divide both sides by 20, and I get that lambda equals 2 pi over 20, which is pi over 10, which is, well, 0.3142 meters. Right. The next question is going to be, what is the frequency? And to figure out the frequency, we're going to use a very similar approach to figuring out the wavelength. What we're going to do is we're going to match up the part here, 2 pi over the period, with the 100 right there. Okay, so using the fact that 2 pi over the period, 2 pi over capital T, matches up with 100, gives us what we need. All right, so here we go. We've got 2 pi over T equals 100. Now keep in mind that the frequency is the reciprocal of the period. All right, so what we do is we solve for the period. So the period is 2 pi over 100. The frequency will be the reciprocal of that. So it's the reciprocal of 2 pi over 100. Well, the reciprocal of 2 pi over 100, I skipped a step here, is going to be 100 over 2 pi. And then 100 divided by 2, okay, that's where the 50 came from. So we have the frequency is 50 over pi, which in decimals works out to be 15.92 hertz, or cycles per second. Okay, next comes the question of velocity. And for this, you need to know a handy formula. All right, so this is something that you're going to be using. When you have this kind of setup here, and the T, remember, is the reciprocal of the frequency. This represents a wave going at a particular speed. And so that is what this is about. So the speed is, so V, the speed of a wave is equal to lambda over the period, which is the same thing as lambda times the frequency. I like this version of, I mean, they're both correct, but this version of it is maybe a little more quick to work with, because you get the right answers right away. You get, so lambda, which was something we figured out up here. I'm going to plug that in. Here's my lambda. It goes in here. And then here is the frequency that we figured out here. Okay. And we multiply and we get 5. And the units are meters per second, right? It's a speed. So it has to be meters per second. And it does work, because here's your meters, and hertz are the same thing as 1 over seconds. Now, remember, this is cycles per second, and so potentially there's confusion going to happen, because in the previous chapter we were really focused on radians per second, but for this formula to work, it's not going to be radians per second. It's got to be cycles per second. Okay, so here we are coming to the end of this video, and I have an exercise for you. What I want you to do is take this description of a wave and answer these questions. It is cosine 1.5x plus 200t. What direction is it moving? What is its wavelength? What is its frequency? And what is the wave speed? And the answers were back at the beginning of this video. All right, so good luck. I want you to figure this out. And if you didn't figure it out, or if you got the wrong answers, you need to figure out why. All right, thank you. Bye-bye.